Welcome to lesson 5. Today's lesson is all about volume and temperature in a gas, or Charles's law. Firstly, I would like you to quickly answer questions 1, 2, and 3. Pause the video now and answer these questions. Okay, so Boyle's law from 2 lessons ago was that pressure is inversely proportional to volume for a fixed mass of gas at constant temperature. Question number 2, the pressure law is that pressure is directly proportional to temperature for a fixed mass of gas at constant volume. Isobaric means constant pressure. Isothermal means constant temperature. Adiabatic means with no exchange of energy or matter with the surroundings. So an adiabatic process does not heat up or cool down the surroundings. It basically happens within a sealed, isolated system. Isochoric means the same as isovolumetric, which means the same volume. So can you actually have these changes? Isobaric, same pressure, you can. So imagine inflating a balloon. The pressure on the outside of the balloon is constant. It's the atmospheric pressure. So the changes inside the balloon effectively happen isobarically. I mean, obviously, you could argue the rubber is applying force, but we're simplifying it. These changes are easy to have. Isothermal is fine. Usually slow changes, so that if the temperature of the system does change, if it does increase or decrease, if you do it slowly, then the temperature has time to equalize. Adiabatic, no energy change with the surroundings. These are very hard to achieve. You basically have to do it extremely quickly. If you make the process happen so quickly that the temperature rise, the energy loss or the energy gain doesn't really have time to have effect, then we can kind of approximate it as adiabatic. Isochoric and isovolumetric, these are easy to achieve, same volume. You just make sure the volume is fixed. So you have a very rigid container, for example, that you can heat the temperature, change temperature in, for example. So how are volume and temperature of a gas related? Should hopefully be fairly obvious that volume is directly proportional to temperature, as long as we are using a Kelvin scale. Just like last lesson, it's only directly proportional if the temperature is in Kelvin. If it's in degrees Celsius, it looks like this. It's a linear relationship, more equals mx plus degrees. So again, if you can again, if you work out x, then you will have some data points up here on the right hand side, and then you're going to extrapolate back all the way down here, work out absolute zero. So units, incredibly important. So volume being proportional to temperature means that this is true. Volume over temperature is a constant, or volume equals constant times temperature. Again, obviously the mass and pressure must be constant. The volume of a gas absolute zero is a good question. We generally say it's the minimum volume. We do say it is zero volume, but in reality, it's probably never going to be zero volume, is it? But effectively the minimum volume. So here's a question for you to try. Pause the video now and complete this question. So relatively simple, as long as you remember to change to Kelvin. So volume over temperature is a constant. The initial volume over the initial temperature must therefore be equal to the final volume over the final temperature. Convert everything to Kelvin, plug in the numbers, and you should get 0.098 meters cubed. All right, question 2. Pause the video now and try this question. So again, volume over temperature is a constant. So it's basically plugging in the numbers, but making sure we've converted to Kelvin. Because we are looking at a ratio of the volumes, it doesn't matter that it's in milliliters in this case, because the milliliters will just cancel when we do volume over volume. So we don't need to convert. Sometimes you might, but not in this case. If you did need to convert, hopefully you remember that 1 milliliter is 1 centimeter cubed, and there are 1,000,000 centimeters cubed in 1 meter cubed. Okay, something a little bit new. How much work is done as a gas changes volume? So if you want to compress a gas, it needs energy to do that. Gas particles don't want to be close to each other. They want to be really far apart from each other, because as soon as they collide with each other, they're going to bounce off in completely opposite directions, and ideally they'll just keep moving away from each other forever. It's only because we force them to be close to each other that they are, either by putting them in a container or by putting so many other gas molecules around them, they stay close. The smaller the container, the higher the pressure, the faster they're going to be moving, and effectively the more energy they are going to have. If the gas expands, it is doing work itself. The energy comes from the gas itself. So as it expands, it cools down. So it is effectively transferring energy out of the system in the form of a temperature drop. So how do we actually quantify that? Well, work done, hopefully you remember, is force times distance moved. This is just the definition of work done. Work done is equal to, or is when a force moves something. And the amount of energy that's transferred is equal to precisely the force times distance moved in the direction of that force. It also means you can nicely estimate a joule. If you get something that is a kilogram and move it 1 meter, you've effectively done 1 joule of work. So how can we apply this to a gas? Because it's very hard to work out the force on a gas or the distance moved of the particles. So we're going to replace force with pressure times area, and that's simply pressure is force over area. Rearrange and substitute in. And so we've got this equation here. Work done is pressure times area times distance moved. And then if you think about an actual piston or an actual syringe moving, as it moves, as the area of it moves along a distance, we've actually covered a volume, because volume is just base times width times height, which is area times height, or volume. So the work done when a gas expands or contracts is equal to the pressure of that gas times by the volume change, or in symbols P delta V. So you'll typically see diagrams like this, where you've got this object here, which is a syringe or a piston. So as this piston moves to the left, it's compressing the gas. We are adding energy to the system or doing positive work. If the gas itself is expanding, so if the syringe moves to the right, the gas is doing work. We say that is negative work. So on the top example, the temperature will increase. The bottom example, the temperature will decrease. So the top one is like a bicycle pump. You'll be pumping up your tires. The bottom one is like a deodorant can. As you press the nozzle down, the gas expands and it cools down. So a question for you to try. Pause the video now and try this question. So what do you need to do? You need to, of course, use this equation. Work done is pressure times change in volume. What is the change in volume? Well, we worked that out in question 2. Well, actually, we worked out the new volume in question 2, which was 714 milliliters. The change in volume is 114. And the pressure, it tells you, is a constant pressure, 3 times 10 to the 6. But now, importantly, because we're doing work done in joules, we do want things in SI units. So we do actually need to change this into meters cubed. So we're going to change by this times by this factor of 10 to the minus 6 because of this conversion mode here. So that is the working out, and that should give the answer of 314 joules. All right, 3 questions for you to think through. So pause the video now and think through these questions. Hopefully, they should be fairly easy to answer based on today's lesson. Obviously, question 1, the temperature is increasing. As the temperature increases, the gas molecules increase the pressure because they are moving faster on average. They're hitting the sides of the container with more force, which means that is the definition of pressure. Question 2, why when you blow bubbles underwater, they expand as they rise to the surface? So as you blow a bubble, that's at a given pressure, the pressure from your lungs. The higher up you go in water, the lower the pressure, or the lower you go, the higher the pressure. Obviously, the lower you go in water, the more water there is pushing down on you. The more water there is above you means there's a greater force in the same area, so a higher pressure. So obviously, as you blow a bubble and it rises, the pressure above it or outside it is decreasing, so the bubble itself can expand because its pressure is going to become closer to the outside pressure. And then question 3, you can type this link in, or I'll put this in the Google Classroom. It's a good video of Chris Hadfield opening a can of Coke on a submarine. So when you go to a submarine at the bottom of the ocean, the pressure inside does increase. Obviously, it doesn't increase as much as it would outside because it would be squashed, but it does increase a bit. So when you open a can of Coke at the bottom of the ocean, it's pretty much completely flat because the pressure outside is so high that it's basically the same as the pressure of the carbon dioxide inside, which means it won't bubble. The only reason cans of Coke bubble is because we are lowering the pressure when we open the can, and therefore the carbon dioxide can dissolve out of solution and form bubbles. This is very similar to the phenomenon of getting the bends, which is a very painful condition that you can get if you go diving. If you dive too deep, more nitrogen dissolves in your blood. And if you rise to the surface really quickly, the nitrogen forms bubbles in your blood, and that can cause horrible, horrible pain, and it can even kill you. It's almost like your blood has become fizzy, although I would never say that to a doctor or a biologist. But it's basically the same as a can of Coke. Okay, part 2, again, is verifying Charles' law experimentally. So this is something we will do at school. Apologize for that. Picture has not come up. When you do the experiment, you will, of course, get this relationship, and you will either extrapolate back with a line of best fit, or probably you are all capable of using maths, and you'll be able to find absolute zero. So the point of this is really to find absolute zero and verify the relationship. How do we do this? Well, we basically get a syringe, a gas syringe. We bought it from the chemists. We heat up a flask of air that's connected to the gas syringe. And as the air inside gets heated, it expands in volume and pushes up the gas syringe. Similar to the pressure law, but we replace the pressure gauge with a gas syringe to measure volume. So very, very simple again, but powerful because it allows us to find absolute zero. So final activity for today. please complete these 3 graphs as a nice summary of the last 3 lessons. Goodbye.